Hello, everybody, and welcome back to session 2 of our meeting here today. My name is Rebecca Hounsell, and I am your chair for this part of the meeting. I'm going to be introducing our wonderful speakers today. We have some great talks lined up. Just a reminder before we get started, if you have questions for our speakers, please either type them in the Zoom chat here or in session 2 on the Slack channel. Our first speaker today is Dr. Philip Macias. He is a postdoctoral researcher at the University of California, Santa Cruz. He will be presenting a talk today entitled An Updated Reference Time Domain Survey and Cosmology Forecast with the Roman Space Telescope. And I'd like to hand it over to you now, Philip. Obviously, if you share your screen, and we will get started. Thank you.
Great. Is that working?
It is, yes.
Awesome. Okay, well, thank you so much, Rebecca, for the introduction, and thank you to the organizers for the opportunity to present. So I'm really excited today to share some of the recent progress that's been underway for the High Latitude Time Domain Survey and share some of the cosmology forecasts with that. So I'll be focusing on the supernova 1A cosmology aspect, but I do want to say sort of within the first few sentences here that in addition to all the cool 1A cosmology and the tons of great supernovae that we're going to observe, there will also be many other transients, non-1As, non-supernovae, and completely unexpected transients to be found along the way in this incredible data set. So I want to emphasize a little bit the process of how we're preparing for the survey, maybe ideally, with the hopes of inspiring some ideas and some preparatory work for others. Okay. So let me just set the stage here by stating the goals. So David did a really great job of sort of motivating why supernova cosmology is important and how much we have to learn about dark energy. And so I will also say that, of course, the top level goal of the supernova survey is to understand dark energy better. And we can quantify how well we can constrain the nature of dark energy, specifically its equation of state, through this dark energy figure of merit. And there are a lot of ways to define this and a lot of ways to calculate it in practice. But I think one easy way or one qualitatively useful way to think of it is shown in this plot on the left here. So this is a plot from Rebecca's paper in 2018, where they show 3 different possible supernova survey strategies for Roman. And they're just showing the constraints that they can place on the equation of state of dark energy today. This is W0. So in standard lambda CDM, W0 would be -1. And on the y-axis, the constraints on WA, which, as David mentioned before, is sort of this way of parameterizing any possible redshift dependence for the equation of state. So with these contours, one way to calculate the figure of merit is just to invert the area. So you can say that the tighter constraints you're placing, the smaller area you have, the larger your figure of merit. And we have an actual number, we have an actual goal. As David mentioned, the goal was to increase the figure of merit by an order of magnitude, which at the time is 32.5. So we have this number, which we're trying to reach 325. And this goal sort of exists in theory space. So Ben made this very nice plot of translating this into sort of data requirements. And so you can think of this as the figure of merit gives you some allowable deviation from lambda CDM. And so you can just think about possible expansion histories within that contour that you're allowed. And that's what's shown on the right. Particularly what's shown is the difference in those expansion histories between standard lambda CDM and a couple of examples here. And so the point to take away from this is that if we want to be able to make these kinds of constraints on the equation of state of dark energy, we need to have few millimag precision across a very large redshift range. And so that is sort of the technical challenge, but is something that will be able to be met with Roman. So that's super exciting. So we have our goal, we have our constraints, and the question is, how do we come back and say, okay, we have a survey design that will be able to meet all of these things. We certainly can't wait until launch. And so the way that we do that is by simulating. And so we are using the supernova analysis package, SNANA, and I wanted to briefly go through how this is done, just because I think it's particularly elucidating. And again, this SED model, in my mind, I'm thinking of 1As and core collapse supernovae, but this process of generating these catalog level simulations is generic to any kind of transient. So the way that it works is you have some source SED, which you then sort of apply all of the effects that would happen to that SED or to those photons on their way from the source to you. So these are things like extinction, et cetera. You integrate across your filters. And this is then convolved with a noise model, which I sort of think of as taking into account all the instrumental effects to finally get out a measured flux. And then finally, you convolve that with a trigger model, where you say, you know, this is what would happen in real life or with real data as well, where you say, you know, I'm not going to consider something to be a candidate unless I get a signal to noise above the background in, you know, one filter above some number or something like that. So you can just decide your own logic there. And those that pass all of this are written out to data files. And so this is what happens sort of on an event by event basis. But then you can imagine convolving this with rates and then saying, you know, given some cadence, et cetera, what does an entire season of my supernova or my survey look like? So this is, again, I just really wanted to go into how the sausage is made here because I think that it can be useful. This is output from a Pippin run. So Pippin is a way to go from these SNANA survey level choices all the way through to this figure of merit. And so I just wanted to show how that's done. So stage one is you simulate the light curves with something like SNANA, just showing here the redshift distribution. I think David showed this earlier. With that, you then fit your light curves. And so this is in the supernova case or in the 1A case, this would be done with something like SALT2. So this is a way to go from, so you fit your light curve parameters in order to get out magnitude. You then have a classification step, which I won't go into detail because Helen will talk in much more detail about this. But of course, this is 1A cosmology survey. And so we only want the things that we're able to standardize. And so again, we will be not necessarily throwing out, but there will be tons of transients that will be discovered and won't be useful necessarily for this cosmology analysis, but that's how we sift them out. I'm skipping a couple of bookkeeping steps here. Oh, right. And so then we have essentially a bag full of light curve parameters. And the question is, how do we get a redshift bin Hubble diagram, which is really what we need to feed to our cosmology fitters at the end of the day. And so we need an expansion history. And the process of going from these light curve parameters to that is not trivial. It's very difficult to propagate forward your uncertainties and take into account contaminants and biases in a statistically sound way, but you can do it. So this is what is detailed in this BBC paper. Then finally, with that, you have some expansion history, and you can throw that off to a cosmology fitter where you say, okay, given this expansion history and some priors, can you please tell me the cosmological parameters that best fit this? So this has been done before. I just wanted to quickly say that Rebecca Hounsel first led this charge a few years ago in doing this for a bunch of different survey strategies with Roman. And we basically are starting off from their most successful strategy. So fast forwarding just a few years, this is a very busy slide. It's intentionally busy, essentially to say that there's a lot of detail in this paper that Ben put out detailing both of the scientific investigation teams' work on the supernova reference survey. So I just wanted to briefly go over the broad strokes of the survey. So it's a two-tier survey. We have a wide tier, which is targeting redshift 1, observing every 5 days in R, Z, Y, and J. The exposure times are determined by this target redshift 1. It's an area of about 19 square degrees. We also have a deep tier, which is targeting redshift 1.7 in, again, every 5 days in Y, J, H, and F to target the rest frame optical. And this is an area of about 4 square degrees. For this baseline reference survey, we are assuming that 25% of our time is going to go to live prism spectroscopy with supernovae. So we will have about 1,500 of those. I won't go into the details about the prism or the spectra because that is what will be spoken about by David next. But here, the point is that we're going to get a lot of supernovae, so something like 12,000 type 1A supernovae and something like 5,000 above redshift 1, which is going to be really incredible. And this is where Roman, we knew, would shine. So here are the filters on the bottom left, and on the bottom right, I'm just showing some example light curves. You can see it, the top left light curve is the wide tier redshift 1. The bottom right is the deep tier at redshift about 1.5. The quality of the light curves is similar, and that is by construction. I think I will skip this but I just want to say that there's a lot more that I am skipping, quite obviously, but there are field considerations, slewing patterns, a lot more detail that can be found in the paper. As I mentioned before, there is a sort of, we are still trying to nail down the fraction of time that can be dedicated to live prism spectroscopy. And there are reasons why you could want more or less time. But the only point that I want to make with this gigantic table is to say that the figure of merit requirement is met across all of these variants that we try. So this 25% is a baseline, but we are actively working to find out what that number should be. And we are also beginning to do preparatory work. So these simulations can also help inform us of things that we need to have sort of in the can before Roman. So this is just an example of where we were looking at the size of a low redshift sample that's necessary to anchor the Hubble diagram because of the degeneracy between the absolute magnitude of a supernova and the Hubble constant. So we wanted to know essentially how long before, or at what size this supernova sample becomes cosmologically saturated in its utility. So it's something about 5,000 supernovae, which we will certainly have in the can before Roman launches, but there are a lot of things to do. And I think this is my final slide, so I just wanted to wrap up by showing, I really wanted to show how this is done, because I think that these are particularly codes like SNANA and pipelines like Pippin are making this sort of experiment particularly flexible and easy to pick up. So yeah, I hope to hear more about exciting things to learn with the supernovas today. Thank you.
Thank you very much, Philip. That was a wonderful talk. I believe we have one very quick question from Ranga Chai. With such large number of greater than redshift 1 supernovae, one should seriously consider using the F213 filter to measure relatively unextinct light curves for at least the brighter ones, because of the difference in sensitivity between F213 and the other filters. So I think that's a comment there from in the session 2 Slack channel. Perhaps you could comment on that, or but potentially type within the Slack channel itself, because we're running out of time right now.
Oh, okay,
so that's what I'm just thinking. It might be better for now to wrap this up and go to our